and welcome to this explainer. Look, if you've been around complex job sites as long as I have, you know that what looks like a simple, everyday hardware choice, like picking a cable tray, can actually be a ticking time bomb for your entire electrical system. We aren't just flipping through catalogs today. Speaking directly from my own experience as a senior supervisor, we're going to expose the critical, hidden dangers of tray selection out there on the site. Specifically, we're going to zero in on the heat dissipation differences between the three main types of trays, and why getting that wrong is so incredibly costly. Okay, let's just dive right in. Here's our quick roadmap for today. We'll be hitting the supervisor's reality, the three core engineering mechanisms, those crucial heat dissipation differences, and finally, managing root transition points. Moving right along. Section 1, the supervisor's reality. Let's talk about the illusion of simple selection. Out on a busy, high-pressure job site, there's this really dangerous illusion that traps even the most experienced contractors. You know the drill. You've got a 300mm route planned, and somebody on site decides to swap a perforated tray for a solid bottom one, simply because, well, it fits the physical space perfectly. But listen to this rule and memorize it. The same 300mm route can justify a completely different tray. Ignore this, and your span and ampacity will absolutely fail. Treating a cable tray like it's just a simple bookshelf, that is exactly how you invite systemic failure. Guys, it is literally never just about width. Which brings us to Section 2, three core engineering mechanisms, or basically the unbreakable rules of tray selection. Since we clearly can't just rely on route width, we have to lean on a strict framework. There are three unbending mechanisms that totally govern your choice here: load deflection behavior, thermal dissipation, and environmental shielding. Now, whenever your cable mix gets upgraded, or your EMC environment shifts, or your fire strategy changes, you have to reevaluate these three things. Load deflection, that just ensures the physical span won't collapse. Environmental shielding keeps the interference out. And thermal dissipation, which is huge, ensures your cables don't literally cook themselves. You really can't ignore even one of these without risking the integrity of the whole install. All right, Section 3, heat dissipation performance differences. This right here is the hidden danger of overheating. This is the exact thermal trap we supervisors absolutely dread. Take a look at the maximum ampacity derating based on the type of tray you pick. A ladder tray? That gives you a minimal, 0 to 10% derating. It breathes beautifully. Step up to a perforated tray and you hit 10 to 20%, but if you use a solid bottom tray with covers, man, you are looking at a massive 20 to 30% ampacity penalty. To put that into perspective, you are trapping all that heat inside a solid metal box, basically choking your power supply and forcing the site to buy thicker, way more expensive cables, all because of a tray choice. So, this sets up a fundamental engineering clash: ladder versus solid bottom. With a ladder tray, you're getting excellent thermal dissipation, but really low EMC shielding. For a solid bottom tray, it's the exact opposite. You are willfully sacrificing that excellent free-flowing thermal dissipation of the ladder tray just to secure the high electromagnetic shielding of the solid bottom. As a senior supervisor, you've got to look at the route and ask yourself, does this specific section run past a high-frequency interference source? If yes, okay, you might actually need solid bottom. But are you prepared to calculate for that 30% thermal hit? Moving to Section 4, managing route transition points. Let's talk about actual on-site execution. So, what actually happens when you're forced to mix these different tray types along a single continuous route? Say a run moves from a nice, cool server room out onto an electronically noisy, hot factory floor. Your tray type obviously has to change, and when it does, you must execute this checklist. Step 1, identify changes in EMC sensitivity. Step 2, assess shifts in fire strategy. Maybe you suddenly need solid walls to prevent fire spread, right? And step 3, the one that gets people into massive, massive trouble. Recalculate ampacity for the new tray. If you transition from a ladder to a solid bottom tray, the thermal environment just changed drastically. If you don't recalculate right then and there, your previously perfectly sized cables are now a serious fire hazard. Because the margins for error are so incredibly tight with these thermal and environmental trade-offs, you absolutely need a manufacturing baseline you can trust. Xinma utilizes really rigorous global standards, stuff like IEC 61537 and NEMA VE1, to build intelligent cable management solutions for demanding environments, like data centers and industrial plants. When you're dealing with a 30% ampacity derating, structural or material inconsistencies simply are not an option. You've got to rely on standardized baseline quality. As we wrap up this explainer, I want to leave you with a pretty provocative thought. Does your current 2026 fire strategy actually account for the thermal trap of a solid bottom tray? Think about the projects you've got slated for next year. Are your contractors treating cable trays just as dumb physical supports, or are they treating them as active thermal and environmental systems? I really encourage you to challenge your current field strategies. Take these insights back to your teams, demand those Ampacity recalculations at every single transition point, and rethink your next major installation. Thanks for joining me for this briefing, and hey, stay sharp out there on the job site.